Okay, so hello everybody. Welcome back. What we're going to be doing today in this video is wrapping up our Chapter 7 lecture on work and energy. So by the end of this video, we'll have covered everything in Chapter 7 that we need to cover. So what we left off with in the previous video was a discussion of variable forces. So how do you calculate the work done by a variable force, that is a force that changes over time? And so what we're going to do next is go over an example of a variable force that's going to come up over and over again in this class, and that's the force exerted by a spring. Okay, so we want to understand what is the force that a spring exerts. So to get a sense of this, I want you to look at the diagram in the middle of the page, and we'll start over here on the left. So what you see is a spring that's hanging vertically, but there is no weight attached to the end of it. In the next picture, we have that same spring, but now we've attached a little bit of weight to it. So the mass that we've connected to the end of the spring here, let's call that M. And we know intuitively what happens when you do this. We know that the spring is going to be stretched out by some amount, and we can actually measure that. So the distance that the spring has been stretched out compared to where we started, that's called D. Okay, so that's the distance we stretch the spring out by putting that weight at the end. So we can continue doing this. Let's say we double the weight. So now it's 2M hanging from the end of the spring. What we're going to find is, if we go over here and look at how much it's been stretched out compared to where we started, now it's 2 times D. So we doubled the weight, and now we've doubled the amount of stretching. And then if we do this again, let's say we hang 3M from the end of the spring, we're going to notice that it's stretched out even more. 3D is the amount of stretching compared to where we started. So hopefully you understand the pattern that's forming here. And this is given by Hooke's law. So Hooke's law describes the force that we're talking about in this scenario. So Hooke's law says, if an external force is applied to a spring, the spring will be stretched or compressed by a distance that is proportional to the applied force. Okay, and that's just an experimental law. If you experiment with some springs and you test out how the amount of stretching depends on the force, you're going to find that it's very simple. It's just directly proportional to the force. So that's exactly what we saw in this example here. Because remember, when we doubled the force, that we doubled the force of gravity acting on the spring, the amount of stretching doubled. And by the same token, when we tripled the force, the amount of stretching also tripled. So it's just directly proportional to the force. Okay, so that's what Hooke's law has to say, but what we want to do next is make that a little bit more quantitative, come up with an equation that says what we've been talking about so far. So to get there, let's first define a variable called x, and x represents the deformation of the spring. So what this means is the deformation of the spring is the change in length from the equilibrium length, and when we talk about the equilibrium length, we're talking about the length of the spring when no force is applied to it. Okay, so here, the first picture you see is a spring with no force being applied to it, and its length is L naught. That's what we call the equilibrium length. Okay, so next, let's imagine we compress the spring, we push it inwards. So now the length of the spring is shortened, it's less than it was before. So the current length L is less than the equilibrium length L naught. So if we do L minus L naught, we're going to get something negative. So when we compress the spring, we say it has a negative value of x, a negative deformation. On the other hand, if we take that same spring and we stretch it out, so now it's longer than its equilibrium length. So L is bigger than L naught, in other words. X is something positive. X comes out to a positive number. Okay? So now that we understand what x is, we can now get an equation for the force that the spring applies. So the force that the spring provides is given by Hooke's law. And Hooke's law says that the spring force, Fs, is equal to minus k times x. So this says exactly what we want it to say. The spring force is proportional to the deformation x, and k is just a constant of proportionality. So k is a constant. But what's the deal with the negative sign? The negative sign indicates that the spring force opposes the deformation. So the spring force goes against the deformation, and for that reason, we call it a restoring force. So let me explain this a little bit more. Let's take the example of the spring being stretched out. So as we saw, x comes out positive when we stretch a spring out. But if we go to the force equation and we plug in a positive value of x here, there's a negative sign out front. So the spring force is going to come out negative. And what that means is the force is in the negative x direction. Okay, so let's try to make some sense of that. In this picture where you're stretching out a spring, you're pulling to the right in the positive x direction. But guess what? The spring is pulling back in the opposite direction in the negative x direction. Okay? So that's what the negative sign in the force is telling us, is that the spring is pulling back in the negative x direction. If we take the example of the spring being compressed, well, we saw earlier that that means x is something negative. But if we apply a negative value of x in our force equation, we're going to have a negative here, but we also have a negative sign out front, so those two cancel, and then we get something positive. So a positive force means the force is in the positive x direction. So let's make some sense of that too. So if you're compressing a spring like this, you're pushing the spring to the left in the negative x direction to compress it. But again, the spring is pushing back against you in the positive x direction. That's that restoring force we're talking about, okay? And that's why there's a negative sign in the equation. All right, so now let's talk a little bit more about the spring constant and what it means. So the spring constant is given by the variable k, and sometimes it's referred to as the force constant, so we'll refer to it both ways. And it tells you how resistant a spring is to being deformed. So let's explain what that means. We're going to start with Hooke's law, which says the spring force is minus k times x. And we're just going to rearrange that equation to solve for k. If we solve for k, we have the spring force, Fs, divided by x. We'll just take absolute values here so we can ignore the negative sign. And really what this is saying is we have a force in the numerator and a deformation in the denominator. Force divided by deformation. And the units, therefore, would be newtons on top, because that's our unit of force, and meters on the bottom, because that's our unit for deformation. It's just some kind of distance. So newtons per meter. Now, there's actually an equivalent unit, which you should know about, which is a kilogram per second squared. So in other words, a newton per meter is the same thing as a kilogram per second squared. I'll show you how that works in just a little bit. But back to the meaning of the spring constant, let's say I have a very large value of k. Okay? That means it would take a lot of force. You need a lot of force to get that spring to deform by some amount. So in other words, large values of k indicate that the spring is very hard to deform. It's very hard to compress it or stretch it out. It takes a lot of force to do that. On the other hand, if k is small, that's indicating that it doesn't really take that much force to get it to deform. In other words, it's very easy to compress or stretch that type of spring when you have a small k value. So to give you just some examples, an example of a small k value would be something like a slinky. Okay, the k value typical for a slinky is something like 1 Newton per meter, so very small. On the other hand, if you were to look at the k value for the springs in, let's say, the suspension system of a car, that would typically be somewhere around 10 to the 5, or about 100,000 newtons per meter. So much larger values of k. Again, those are harder to compress comparatively. Okay, next. let's think about what we can learn about the spring constant graphically by drawing a graph. So on the graph on the bottom right-hand side of the slide, we have on the vertical axis the spring force, and on the horizontal axis we have the deformation, x. And again, we know what the relationship between these two is. It's given by Hooke's law. So the spring force is just k times x. Again, just using absolute values, ignore the negative sign for now. And k times x is just an equation for a straight line that goes right through the origin. And remember that whatever goes in front of your x variable, whatever that constant there is the slope. So in other words, the slope of this line is the spring constant. So if you make a graph of the spring force versus the deformation, it's the slope of that line that gives you the spring constant. And then before I forget, let's do a quick side note on units. Okay, so remember K is measured in newtons per meter, but we also remember from F equals ma that the unit of force, which is a newton, is the unit of mass, which is a kilogram, times the unit of acceleration, which is a meter per second squared. So in other words, a newton is the same as a kilogram times a meter per second squared. And then we're dividing that by m. So notice how units of meters just cancel out, and you get kilograms per second squared. So there's an equivalency between these two units. That's what I was talking about earlier. So next, let's do an example. Let's calculate the work done to stretch a spring out. So let's suppose you have a spring that has a force constant of 1.20 times 10 to the 3 newtons per meter. You stretch the spring a distance of 52 centimeters from its natural length by pulling the end at a constant speed. The question is, how much work do you perform during the first half of the stretch? So what you should be picturing here is we start off with the spring in its equilibrium position, so it's not stretched out yet, but then you grab the end of it and you pull it to the right, and that stretches it out, and the total amount of stretching is 52 centimeters, but what we're interested in is what is the amount of work that you do just during the first half, okay, the first 26 centimeters. So let's work this out. Okay, let's start by sketching out a picture. This is our spring, and if we think about the forces that are being applied to the spring, you're pulling it this way, so we call this F pull, going to the right. But as you're pulling, the spring is pulling back against you with a force we'll call F spring. Now, if we apply F equals ma, Newton's second law, to this situation that I've just sketched out, here's what we'll get. So we have the pull force, and we add that to the spring force. And what we get is actually 0 because the spring is being stretched out at a constant speed. So constant speed always implies A is equal to 0 if we're just moving in a straight line. So there you have it. And the point of that is to say that the pull force is minus the spring force. Okay, so it's just in the opposite direction, but just as strong. And since the spring force is minus kx, well, the pull force is just going to be positive kx. Okay? So the next thing we do is we calculate the work, and this is a variable force. So we have to do an integral. The way this works from the last lecture is you integrate from the initial to the final position, and you plug in the force, and you integrate that. So again, the force we're dealing with here is k times x. So I'm going to plug in k times x into my integral. And then I'm also going to note that I have a constant. So k is constant. And we're always free to pull constants out of integrals. So now I have k out front, and then x initial to x final, x dx. So this is a pretty simple function to integrate. We have k out front. Use the power rule. So for integration, we have x to the first power starting off. So we have to raise the power by 1. So now we have x squared. But we have to divide by that same power. So now we have a half out front. And we evaluate this from x initial to x final. So in other words, 1/2 k are the constants that I have out front. Plugging in the upper limit, I have x final squared. And then subtract x initial, which is my lower limit, and square that. So at this point, we can just go ahead and plug in some numbers. So the work that you do in pulling this spring is equal to 1/2. K value is 1.2 10 to the 3 newtons per meter, but again, that's the same as a kilogram per second squared. If we're only interested in the first half of the stretch, we're only going to 26 centimeters, so 0.260 meters. And the x value we start with is 0 because it's initially not even stretched out. Okay, so if you do this calculation, I'm going to find it comes out to about 40.56 units. We have our kilograms, we have meters squared, and then we have seconds squared on the bottom. And if we round this to the right number of sig figs, which would be 3, we'd have 40.6 joules. Because remember, these are the same unit. A joule is a kilogram meter squared per second squared. So it takes 40.6 joules worth of work to stretch the spring out for that first half. And here's a follow-up question that I'd like you to try to work out on your own. So same scenario, we have a spring with a force constant of 1.2 times 10 to the 3 newtons per meter, and you stretch it out 52 centimeters from its natural length. Question now is, how much work do you perform during the second half of the stretch? So in other words, if we're already here at 26 centimeters, how much work does it take to do that second half to get to here? So try to work this out, pause the video, and then come back to the video to see if we agree on our answers. Okay, so to work this one out, we can use the same expression for the work that we derived in the previous example. So it's a half k times x final squared minus x initial squared. This is still a valid expression to use. It's just that x initial and x final are going to change compared to what we did previously. So we have a half. The k value is 1.2 10 to the 3 kilograms per second squared. Now this is the second half of the stretch, so where we end up is the final position, which is 52 centimeters, or 0.520 meters squared. And we start off at 0.260 meters, and we square that, or 26 centimeters. Okay, so this is for the second half of the stretch. This is how much work you need to do. And this works out to 121.68. Units are kilograms, meters squared divided by seconds squared. But we want to round that to 3 sig figs, which is about 122 joules. Now, we could just end it right there, but I do want to show you a different way to think about this problem that gives you a little bit more insight. And that's if we go to the graph. So we have force that you're pulling with over here, and we have x on this axis here. And we know what this looks like. It's just a straight line. So this line is just kx. And if we kind of divide this into two parts here, let's say this is where we end up. stretched out by 52 centimeters. And then this is where we start. We start over here at 0. And then the halfway point is 26 centimeters over here. We can call the work done in the first half of the stretch W1, and the work done in the second half of the stretch W2. And remember, work is given by the area under the F versus X graph. So the area under this graph gives us the work. Okay? So the work that we calculated before is this area, which goes from 0 to 26 centimeters. And the work that we just calculated for the second half of the stretch, I'll shade it like this, is the area under the graph between 26 and 52 centimeters. Now I want you to notice something about how these two areas that I've drawn relate to each other. So if we look at W2, that area, well, part of it is a little triangle that looks like this, which is equivalent to W1. And then we can actually make two more of those triangles by splitting this little rectangle down the diagonal. So we'll have another area like this and another area like this. So if we think about the work as area under the curve, it's pretty clear that W2 should be 3 times W1. In other words, the area under the curve between 26 and 52 centimeters is 3 times the area under the curve between 0 and 26 centimeters. So in other words, we should be getting 3 times what we got in the previous example. So let's see if that works out. 3 times 40.56 joules gives you 121.68 joules, which we round to 122 joules. So that's how you think about the problem graphically, okay? All right, so we've seen Hooke's law. You've done a couple examples, so hopefully now you have a pretty good sense as to what that's all about. But you may be wondering, why are we spending so much time talking about springs? You know, if we want to understand the world around us, it's not like you just go outside and you find springs lying all over the ground. It's not like they're a feature of the natural world. And that's true. So Hooke's law actually is a little bit more general than just an equation that talks about springs. In fact, we can use Hooke's law to understand elasticity in materials. Okay, so the fact that materials can be elastic. So to understand this, take a look at the diagram on the slide here, which is a model of a solid. Okay, so in this model, each atom in the solid is a mass, and to model the forces between the atoms, we pretend like the atoms are connected by little springs. So it's not as if there are literally springs connecting the different atoms, but it's just that the forces between the atoms are actually pretty well described by Hooke's law. So in other words, this model of a bunch of masses connected by springs does a really good job of describing a solid, a real solid. So what are some of the features of this model? Well, each atom has an equilibrium position. Okay, so it's the position it will have if there's no outside force applied. But let's say there is an outside force. Maybe you come along and you squish the solid, you compress it, okay? Well, that's going to cause the atoms to move away from their equilibrium positions, right? But as soon as you take that external force away, you stop squishing the solid, then these springs will push back out and bring the atoms back to their original positions. And that's what really elasticity is. It's the fact that if you take something and you squish it and then you let go of it and you remove that force, it goes back to its initial position. Or if you stretch it out and then again you remove the force, it goes back to its initial position. You can understand that pretty well using Hooke's law. are actually a lot of other things you can do with this kind of model of a solid. You can understand how sound moves through materials, and even things like heat and temperature using a model like this. So we're not really going to get into any of that, but I wanted to point out that Hooke's law is very useful and it has much more general applicability than just talking about springs, okay? So it's not really, strictly speaking, about springs. It can be used in a lot of different ways. Okay, so the next topic is the work energy theorem. Now, up until this point in the lecture, we've mainly been talking about different ways to calculate work, okay? And that's an important thing. You do need to know how to calculate work in different situations. But what we haven't really talked about yet is why. Why do you need to know about work? Why is this a useful concept? And how can we actually apply it? So that's what's coming next. But to get there, we first need to define something called kinetic energy. So kinetic energy is the energy associated with the motion of an object. So what we say is an object has kinetic energy by virtue of its motion. So there's a formula, which we're going to learn about right now. K, capital K for kinetic energy, is equal to 1/2 mv squared, where m is the mass of the object and v is the speed. So you can see that the faster something is moving, the more kinetic energy that it will have. So the SI unit of kinetic energy is also a joule. And let's see how that works out real quick. So we know that the unit of mass, so the m term in the equation here, is going to be measured in kilograms. And the SI unit of speed, that's v here, is a meter per second, but we're squaring that. So we get a kilogram times a meter squared per second squared, and we already know that that's equivalent to a joule. Okay, so the SI unit of kinetic energy is a joule. Let's do a couple examples just so we get some practice calculating kinetic energy. The first example is, how much kinetic energy does a 4.2 gram bullet traveling at a speed of 965 meters per second have? The second example is, how much kinetic energy does a 125 kilogram linebacker running at a speed of 6.5 meters per second have? So let's work each one of these out. Okay, so for both of these calculations, we're going to be using K is equal to 1/2 mv squared. That's just the definition of kinetic energy. And let's start with the bullet. So in the case of the bullet, the mass was 4.20 grams. We better convert that to kilograms though to get the result to work out in joules. So 4.20 times 10 to the minus 3 kilograms, that's equivalent to grams. And then the speed was 965 meters per second, but we have to square that speed. Now, what this works out to is 955.6. Round that to 3 sig figs. Units are kilograms, meters squared per second squared, but we already saw that's equivalent to a joule. So to round it off to the right number of sig figs, we have 1,960 joules. Okay, for the linebacker, the kinetic energy is going to be given by the same formula, but this time the mass is 125 kilograms, and the speed is 6.5 meters per second. And when you calculate that, you get 2,640.6. We'll keep 3 sig figs, again, kilograms, meters per second squared. That's the same as a joule. So 2,640 joules for the linebacker. So that may be a little bit surprising that a person just running down a football field can have more kinetic energy than a bullet. But the point is, this energy of the bullet is packed into a much smaller space. So that's why it's much more dangerous. Okay, and now we're here at the work energy theorem. So There is a derivation given of the work energy theorem in the textbook. I'm not going to go through that in today's lecture. Instead, what I want to focus on is what is the work energy theorem and what is it saying, and then how can we put it to use. So the work energy theorem says that W net is equal to delta K. Okay, so W net means the total work done by all of the different forces acting on an object. Remember, we have ways of calculating work, and we have to do that for every single force acting on the object and add those together to get W net. Okay? Then on the other side of the equation, we have the change in the object's kinetic energy. So the net work done by all forces is equal to the change in kinetic energy. That's what this is saying. Okay, so let's look at a couple different cases that might arise. If the net work done on an object is positive, then that means its kinetic energy is increasing. So it's speeding up. In other words, positive work automatically gives you a positive kinetic energy change, meaning we're speeding up. And that should make sense because if you remember, work is positive whenever the force is going with the motion. So if you apply a force that's going with the motion of an object, you expect it to speed up. Let's go back. On the other hand, if the work is negative, okay, then kinetic energy is automatically going to be decreasing. In other words, negative values of W automatically imply negative delta K. Again, this should make sense. When work is negative, if you remember, this means the force is going against the motion. If you apply a force against an object's motion, you do expect that it's going to slow down. On the other hand, and the last point here is, if the net work done on an object is 0, then the kinetic energy doesn't change. So in other words, if W is equal to 0, that automatically implies delta K is equal to 0, meaning the kinetic energy is not changing. That means the object is just moving along at a constant speed. Okay? So these are the three cases you should kind of have in the back of your mind. Okay, here's a conceptual question for you. Let's say that you're swinging a ball attached to a string in a circular path. And let's imagine that you're doing this in completely empty space so that there's no gravity acting on the ball. The tension in the string is 50 newtons, and the radius of that circular path is 1 meter. The question is, what is the change in kinetic energy of the ball, that's delta K, after it makes one full revolution? So this is the motion that you should be imagining. We're just swinging this ball, and there's a constant tension in the string, but otherwise there's no other force acting on the ball because there's no gravity or anything like that. So what's the answer? What's the change in kinetic energy? Use the work energy theorem to try to figure this out. So pause the video, see if you can come up with your answer, and once you think you have it, come back to the video and we'll talk it over. Okay, so let's start by drawing a picture of the motion of this ball. So it's moving in a circular path, something like this. And let's say the ball is over here on the right side. So the tension in the string is going to be pulling the ball in. Remember, tension always acts along the length of a string. So there's our tension force. But if we think about which way the ball is moving, it's moving tangent to the path. So our displacement, let's say we're talking about a tiny little displacement dr, that's going to be tangent to the path. So we know that the work is the integral of f dot dr. That's the most general way to think about it. And in this case, that dot product is going to be 0 because the force and the displacement are at 90 degrees. So in other words, they're perpendicular. Whenever that's the case, the work comes out to 0. Well, the work energy theorem tells us that W net is equal to delta K. So if there's no work being done on this ball, there's no change in kinetic energy at all. So in other words, the ball is just rotating at a constant speed. Its kinetic energy is not changing. All right, let's take a look at another example. In this case, we're going to be moving a box across the floor. So starting from rest, you pull a 30 kilogram box a distance 6 meters across the floor by applying a force of 200 newtons at an angle of 30 degrees above the horizontal. Okay, so you're pulling at an angle of 30 degrees, just like is shown here. Now, there is friction. So the coefficient of friction between the box and the ground is 0.15. So what we want to do is calculate the work for each force acting on the box. Okay, so for every single force that's acting on the box, we're going to calculate the work. Then we're going to add those numbers together to get the net work done by all the forces. And then, as a final step, we're going to use the work energy theorem to find the final speed of the box after it's moved 6 meters. So this is just an example of how we can use the work energy theorem to predict how something is going to be moving. So let's work it out. Okay, so there are a lot of different steps in this problem. So what we should start with is a free body diagram of the block, because we need to know all the different forces that are involved. So let's say this is the block. We know there's a force P acting on it, which is the force you're pulling with. We also know that this force is at an angle of 30 degrees with respect to the horizontal, like that. We also know there's a force of gravity, which points straight down. That's always going to be present, so that's Fg. Also, this box is resting on some kind of surface, so there must be a normal force, N, which points up away from that surface. And lastly, we know there's friction, and the friction will oppose the motion. So it's kinetic friction in particular, Fk. The displacement of the box is to the right. So this is the direction we're moving in. And these are all the different forces acting on the box. So we have a total of 4 different forces. What we're going to do is for each force, we're going to use the formula W is equal to Fd cosine of phi. And we can do this because we're dealing with constant forces. None of these forces is changing over time. So how about we start with the normal force? Let's find the work done by the normal force. The way this works is we take the magnitude of the force, which is N, times the distance we move, which is D, and then cosine of phi. And remember what phi means. It's the angle between the direction of motion and the force. Well, in this case, the normal force is at 90 degrees to the direction of motion. Okay, because we're moving to the right and the normal force is straight up. So that's a 90-degree angle. This is going to give us 0 because cosine of 90 works out to 0. Do something similar with the force of gravity. The work done by gravity is going to be the force of gravity times the distance. But again, the angle between the force of gravity and the direction of motion is 90 degrees. So we get 0 for that work also. Okay, for the work done by the pull force, well, that's going to be the force that we're pulling with P times the distance we move times cosine of 30 degrees. Okay, so in other words, the direction of the pull force is at 30 degrees to the direction of the displacement. Okay? And at this point, we can just plug in some numbers. So we're pulling with 200 newtons of force. The distance we move is 6 meters. And then, of course, we have cosine of 30 coming along for the ride like this. Now, what this works out to is 1,039 Newton times meters are the units here. But we do want to round this off to 3 sig figs, so we would say 1,040 joules. And remember, a Newton times a meter is the same as a joule. There's only one left, okay? We need to find the work done by friction, because here, we've got the normal force, we did that, we've got the pull force, we've got gravity. What's the work done by friction? Well, this one's gonna take a little bit more effort, because the first thing we need to do is figure out what the force actually is. Okay, so I want to remind you a few things. Fk, force of kinetic friction, is given by mu k times n. So it's that friction coefficient times the normal force. So we better figure out what the normal force is. How do we figure out what the normal force is? Well, we can do F equals ma. We can apply Newton's second law to the block. And we can focus on the y direction because the normal force is in the y direction. And so the normal force is going up, straight up, so that's just a positive n. Force of gravity is going straight down. And then we also have the y component, I'll indicate that right here, the y component of the pull force going straight up like this. And on the other side of the equation, we have the acceleration in the y direction, which is 0. So there's no vertical motion. Which is why we can set the acceleration in the y direction equal to 0. Okay, so to solve for n, we have force of gravity minus py. And by the way, the force of gravity is just mg. And the y component of that pull force is going to be p sine 30 degrees. So that's how we calculate the normal force. So let's do it. The mass, m, is 30 kilograms. G is 9.8 meters per second squared. And then we're subtracting, P is the pull force, 200 newtons, but we have to multiply by sine of 30 degrees. So the normal force we're getting out of this calculation is 194 newtons. Okay, so all that work there was just to solve for the normal force. Then once we have that, the friction force is just, again, mu k times that value of n. So we have 0.150 is our friction coefficient. We're multiplying that by 194 newtons. And so the friction force, therefore, is 29.1 newtons. Okay, now we're ready to calculate the work done by the friction force. Again, it's the same formula for work that we were using before. We're going to take the force itself times the distance times the cosine of the angle between the force and the displacement. Now notice that in this case, since we're dealing with friction, the force goes exactly against the displacement. So the angle between them is 180 degrees. So we have cosine of 180 degrees for this one. So now let's just plug in what we know. Friction force, 29.1 newtons. Distance, 6 meters. And then cosine of 180 works out to -1. So friction is doing negative work. This makes perfect sense. Friction is always going to do negative work because it slows things down. Okay? So this works out to negative 174.6 newtons times meters, but again, that's the same as a joule. And if we round it off to 3 sig figs, that's 175 joules, or sorry, negative 175 joules. Okay, so the next part is we're going to calculate the net work done by all of these forces added together. So we have 4 different things to add. We have the work done by the normal force, we have the work done by gravity, we have the work done by the pull force, and then we have the work done by friction. But luckily for us, we found the normal force doesn't do any work and neither does gravity, so we're just worried about those other two terms. So we have 1,039 joules for the work done by the pull force, and then we have negative 174.6 joules done by friction. Okay, so if you do that calculation, you're going to get 864.4 joules. That's the net work done by all the different forces. But actually, if we're really keeping track of our sig figs, we have to round to the tens place because that's where we rounded for our first number here. So this would round to about 860 joules. Okay, so that's the net work. The last part of this is now we can use the work energy theorem, which says that W net is equal to delta K to solve for the final speed of the box after it's moved 6 meters. Okay, well, delta K is a change in kinetic energy. So we have 1/2 mv final squared, that would be the final kinetic energy, minus 1/2 mv initial squared, but right away we can cross this term out because we know the initial kinetic energy is 0 whenever we start from rest. And so, to find V final, we can solve for that. V final squared is equal to 2 W net divided by M. So, of course, if I want V final, I'll have to square root both sides. So I'll have the square root of 2 W net divided by M. And here's what we get. The final speed is the square root of 2 times W net was 864.4 joules. And the mass of the box, M, was 30 kilograms. This works out to about 7.59 meters per second, but we'll round that to 2 sig figs to 7.6 meters per second. That's the final speed. Okay, so this was kind of a complicated problem, a lot of stuff going on, but hopefully you see how we can use the work energy theorem to make predictions about how things move. All right, so in this next example, we're going to be revisiting projectile motion, which is something that we learned about back in Physics 44. And we spent a lot of time on this, actually. And in particular, we learned about kinematic equations that we can use to solve problems in projectile motion. So now what we're going to be doing is applying this new technique, this new concept, the work energy theorem, to the problem of projectile motion. And hopefully what you'll get out of this is you'll see that in physics, there are often many different techniques, many different physical principles you can use to solve a problem. And this is just one of those examples. So what we have here is a projectile which moves with no air resistance from position 1, which is down here, to position 2, which is up here, and it moves along this path to get there. What we want to do is find an expression for its change in kinetic energy. So to remind you, the work energy theorem says that W net is equal to delta K. That's what we'll be using. We want to find delta K, the change in kinetic energy. So delta K is equivalent to the work, and remember that the work can be expressed as the integral of F dot dr. So that's what we're going to be using to calculate work. By the way, there's only one force acting on this projectile. Again, there's no air resistance. So the only force we have to keep track of is gravity. And the force of gravity is a downward force. If we write it in component form, that would be 0 I hat, so there's no x component to gravity. The y component is negative because it's going down, and mg j hat is how we write that. Okay, what about dr? That's a displacement, and in particular, it's a little infinitesimal displacement along this path. The way we can write this in component form is dx I hat plus dy j hat. So basically what we're saying here is as the projectile moves, it has a little displacement along the x direction, and it has a little displacement along the y direction. So what we're going to do is take the dot product of that f vector and that dr vector inside of our integral. And remember how dot products work when we have things written in component form like this? What we do is we multiply the x components together. So 0 times dx, that just gives you 0. And then we multiply the y components together. So we have minus mg and then dy. So what we're left with in the integral is minus mg times dy. But we'll also notice that minus mg is a constant, so you can just pull that out of the integral. So what we have is minus mg times the integral dy with the limits going from y1 to y2. So y1 and y2 are just the starting and ending heights of this projectile. Now that's a really simple integral. If you work it out, it just comes to y2 minus y1. So we have minus mg times y2 minus y1. And if you want to write this in a more compact way, y2 minus y1 can really be thought of as delta y, the change in height. So what we have is the change in kinetic energy, delta K, is minus mg delta y. Okay, so that's the result. The change in kinetic energy is only going to depend on the change in height. And let's look at a few cases. So if delta y is positive, okay, if delta y over here is positive, that means the projectile is moving upwards. So it's gained some height. And we know intuitively that if a projectile is on its way up, it's slowing down as it moves upwards. Well, that's exactly what this equation tells us, because if delta y is positive, we have a negative sign here. So delta k will end up being negative. Okay, so this says as a projectile moves up, it's losing kinetic energy. Okay, so because delta k is negative. The other case we can look at is if delta y is negative, that means the projectile is moving down. And in that case, we have a negative delta y, but that negative sign cancels with the one out front. So our delta k ends up being positive. And what that's saying is when the projectile moves down, it gains kinetic energy. That's pretty intuitive, right? If a projectile is on its way down, we know it's speeding up. Okay, so that's exactly what this result is telling us. So let's use the result that we just derived, and I want you guys to try to work out this problem. So a rock is thrown off the edge of a cliff, which is 140 meters tall, with an initial speed of 25 meters per second. What is the speed of the rock just before it hits the ground? So try to work this one out. Pause the video and come back to it once you have an answer, and then compare it to what I do. Okay, so let's sketch out the situation. We have a cliff. The height of this cliff is 140 meters. And what we're doing is we're launching a rock from the edge of the cliff at an initial speed of 25 meters per second. And we know it's going to move in an arc and hit the ground over here somewhere. What we're interested in is how fast is it moving just before hitting the ground. We don't know the final, in other words. So right off the bat, let's just note that delta y for this rock is negative 140 meters because overall throughout this motion, it's moving down 140 meters. So delta k is equal to minus mg delta y, that's what we just derived. And recall that kinetic energy is 1/2 mv squared. So delta k would be 1/2 mv final squared minus 1/2 mv initial squared. And then that would equal minus mg times delta y. Cancel out m. And also, since we're solving for v final, let's put the 1/2 v initial squared on the other side of the equation. So we have 1/2 v final squared equals 1/2 v initial squared minus g delta y. And then just multiply through by 2. So v final squared is equal to, cancel out the 1/2 over here, so it's v initial squared minus 2g delta y. And of course, we'll just square root that to get the result we want. So v final is the square root of v initial squared minus 2g delta y. And we'll plug in what we know. V initial is 25 meters per second. We'll square that. Minus 2 times g, which is 9.8 meters per second squared, times delta y, which is minus 140 meters. So you make this calculation, and you should get 58 meters per second. So using the work energy theorem, we were able to figure out that the final speed of this rock just before it hits the ground is 58 meters per second. Okay, let's do another example. So in this one, we're going to be dealing with a variable force and incorporating the work energy theorem along with that. So we have a 6.75 kilogram object moving in one dimension, so it's just moving on the x-axis, and it's subject to a single force, which changes with position according to the graph on the left. So this graph right here is basically describing how the force on the object is changing over time. So the object starts at the origin, that's x equals 0, with 0 speed. What will its speed be at x equals 4 meters? What will its speed be at x equals 7 meters? We're going to use the work energy theorem for this. And again, the idea is the object starts off over here at the origin and it's at rest. But there's a force acting on it, so it's going to end up over here sometime later, moving at some speed, and we want to figure out what that is. And then sometime after that, it's going to end up over here, and we want to figure out what the speed is when it reaches that point also. So let's work this out. So we'll start with the work energy theorem, which says W net is equal to delta K. And in this case, we're dealing with a variable force, so the work is going to be given by an integral. Okay, we're integrating the force over x. But we'll also remember, that the integral is the same as the area under the curve of the f versus x graph. So for our purposes, it's going to be a little easier to calculate the work by just finding the area under the curve. So there are two parts to this. The first part is we're going from x equals 0 to x equals 4 meters. And in that case, what's the work? Well, that's basically the area under the graph from here to here, from 0 to 4. And we can take this area to be in two parts. We have a rectangular area right here, and then we have this triangular area right over here. The rectangular area is just the base times the height. So that base would be 3 meters. So we have 3 meters in this direction. The height would be 6 newtons. And for the triangular area, that's 1/2 base times height. In this case, the base is just 1 meter. And the height is the same as before, 6 newtons. Okay? So basically what we have is 18 plus 3, which is 21 newtons times meters, or 21 joules. Okay, so we know the net work that's done going from x equals 0 to x equals 4. So now, if we apply the work energy theorem that says W net is equal to delta K, well, delta K, as always, is 1/2 mv final squared, final kinetic energy, minus 1/2 mv initial squared. But here's the thing, at the start of the motion, at x equals 0, we know that the object is at rest. So we can set the initial kinetic energy to 0, because it's at rest starting off. And so we can calculate VF, V final, just by rearranging the equation to say that V final squared is 2 times W net divided by M. Of course, we have to square root both sides if we want to just get VF by itself. So what we have is the square root of 2 times 21 joules, which by the way is a kilogram times a meter squared per second squared. That's how you break down joules into the base units. And then what's the mass of our object? The mass, yes, is 6.75 kilograms. So notice what happens to the units. Kilograms go away. And then when we square root it, we're going to be left with meters per second. And if you round it off to 1 decimal place, this works out to about 2.5 meters per second. Okay, so in the next part, we're going from x equals 0 to x equals 7 meters. And here's what we have to do in that case. We're going to keep calculating W net as the area under this curve, but now we have some negative area. That's how this works when your graph goes below the x-axis. You have to count this area as negative. So now we're going to add this little bit of triangular area right here. And to get all the way to 7, we have this little square area right here that we have to add. So here's what we have for the area under the curve, okay? We have the same rectangular area to start off right here, which again has a base of 3 meters and a height of 6 newtons. And then we have that same triangular area right here, which is 1/2 base times height, where the base is 1 meter. Actually, let me write this down here. So 1/2 base times height, the base is 1 meter, and the height is 6 newtons, just like before. Okay, then we have this negative area right here. We have to subtract that area, and the base is 1 meter, and the height is 6 newtons, just like before. And then finally, we have some negative area right over here. And in this case, the base is 2 meters, and the height, so we're subtracting that, the base is 2 meters, and the height is 6 newtons. Okay, so basically, the area under the curve from 0 to 7, I break it up into these 4 parts. And again, we have to count negative area for the stuff that's under the x-axis. And when we do this, we end up with a result of 6 newtons times meters, which again is 6 joules. Okay? So in this case, if we want to find the final speed, it's the same as before. We can use the square root of 2W net. 2W net divided by the mass, just using what we found over here. And so what we have is the square root of 2 times 6 joules, which again is kilograms meters squared per second squared. And we'll divide by the mass, which is 6.75 kilograms. Canceling out units of kilograms leaves us with units of meters per second. And if you work this out and round to 1 decimal place, you'll get about 1.3 meters per second. Okay, so that's how this one works. Okay, so let's do one more example using the work energy theorem, and then we'll end the lecture. In this question, we have a hockey puck, which is initially sliding along a flat and frictionless sheet of ice at 3.75 meters per second. The puck then slides up an ice ramp, so it's also frictionless, which is angled at 17.5 degrees relative to the horizontal. How far up the ramp does the puck go before sliding back down? We're going to use the work energy theorem. All right, so this is actually another example where you could probably solve this problem using some technique that you learned back in Physics 44. But again, it's important to see how you can solve it another way with the work energy theorem. So give this a try, pause the video, and then come back to it to see how I work it out. Okay, so we'll start by drawing a free body diagram of the puck. So the puck is on a ramp. There's the ramp. The puck will draw like this. And again, in a free body diagram, we need to just label all the different forces. So gravity always points down. And the normal force always points perpendicular to the surface. In this case, the surface of the ramp is tilted, so our normal force is going to have to tilt in turn, and there we have it. Now, there's no friction, so we've actually accounted for all the different forces. But let's actually label the angle of the ramp right here. So the angle of our ramp relative to the horizontal is right here, 17.5 degrees. And then let's also take note that this is a right angle. Okay, so between that horizontal line and the force of gravity, we have a right angle. Let's also note that we're looking at a puck that's moving this way up the ramp. So its displacement is up the ramp. And so what we're going to do is, for each of these two forces, we're going to use work is equal to force times distance times cosine of phi. And again, it's perfectly okay to use this formula because the two forces we're looking at, the normal force and gravity, are constant. So we can use this for each force. Okay, let's do the normal force. The work done by the normal force is equal to, well, the force is N, the distance we move is D, and in fact, we're trying to find that distance. And then we have cosine of some angle. Now remember, the angle in this formula for work represents the angle between the force and the displacement. So that's actually just 90 degrees. Okay, the angle between our force vector, which is coming out of the ramp, and the displacement vector, which is going up the ramp like this, they're perpendicular to each other. So cosine of 90 always gives you 0. The normal force is not doing any work. What about the work done by gravity? Well, that would be the force of gravity times the distance along the ramp that we move, and then cosine of the angle between the direction that we're moving in and the force of gravity. Well, if we go to our diagram, we can see that the angle we're talking about is 17.5 degrees plus this 90 degree angle to give us this total angle, which I'll just draw right here. That's the one we care about because that's the distance between displacement and force. Okay, so by the way, the force of gravity is given by m times g, so we have mgd, and then cosine of 107.5 degrees, that's the angle. So next, we're going to use the work energy theorem, which says that W net is equal to delta K. And the only force that's doing work is gravity, so we just say mgd cosine of 107.5 degrees is the net work. The kinetic energy final can be written as 1/2 mv final squared. The kinetic energy initial is 1/2 mv initial squared, so we subtract those two. But actually, I can cross off the final kinetic energy. And the reason for that is the puck comes to a stop at the highest point. Okay, so when it reaches that highest point on the ramp, it will momentarily come to a stop and then slide back down. So we can set the final kinetic energy to 0 because we're trying to figure out how far up the ramp it went. So to solve for D, just divide out the mass, so that cancels actually, and also divide out G times cosine of 107.5 degrees. And so here's what we have. We have minus V initial squared divided by 2 because we have this 1/2 factor in front of that. And then we divided out the G and we divided out the cosine of 107.5. So this is the expression we're dealing with. So we have minus V initial, which by the way is 3.75 meters per second, and we square that. And then we divide by 2 times G, which is 9.8 meters per second squared. And then we have cosine 107.5 degrees. And what you get is 2.39 meters. That's how far up the ramp we go. That's how this works. All right, and before we wrap this video up, I just want to remind you that at the end of every lecture, we have practice problems. You don't have to do these problems. They're not for credit. These are just here to help you study. So I have a number of problems dealing with the content from chapter 7 and the work energy theorem and how to calculate work, things like that. So you can do these on your own time if you feel like you need the extra practice, and you can find the answers on Canvas if you want to check that you're doing things right. So a number of problems at the end of the lecture as usual. And with that said, I'll see you in the next video. Until then, take care and be safe out there. See ya.